The Foundations of Boolean Algebra. This document provides a concise theoretical synthesis of the foundational concepts of class algebra, as outlined in Chapter 1. It establishes the elementary ontology necessary for the subsequent formalization of Boolean logic. The concept of classes, sets. The foundational entity in this discourse is the class, or set. A class is rigorously defined as an aggregate of distinct objects. The identity of a class is established either extensionally, through an exhaustive enumeration of its constituents, or intentionally, by stipulating a characteristic property that must be satisfied uniformly by all its members. The principle of extensionality dictates that classes sharing the identical membership are, by definition, equal. This abstraction forms the bedrock of modern set theory and algebraic logic. The membership relation. The primary dyadic relation is membership, denoted by the epsilon symbol, E. This relation specifies the connection between an individual object, the element, and the aggregate, the class. It is an asymmetric relation, stating that a specific entity belongs to or is contained within a defined collection. The negation of this relation is denoted by En. The notation for a class explicitly lists its members enclosed within braces, e.g., A, B, C. The order of elements and the repetition of identical elements within this notation are mathematically irrelevant to the identity of the class. 1.2. The inclusion relation, subsethood. Inclusion, or subsethood, must be categorically distinguished from membership. While membership relates an element to a class, inclusion is a relation strictly between two classes. A class A is said to be included in a class B, denoted A subset B, if and only if every element that is a member of A is simultaneously a member of B. It follows that subsethood is reflexive, A subset A. Furthermore, the axiom of extensionality can be restated using inclusion. Two classes are strictly equal, A equals B, if and only if they are mutually inclusive, A subset B and B subset A. A subclass that is not equal to its superclass is termed a proper subclass. 1.3. The empty and universal classes. The theoretical framework necessitates the postulation of two limit classes. The first is the empty class, or null set, denoted by 0, or empty set, which is defined as the class possessing no members. Consequently, the proposition X is an element of 0 evaluates to false for any given X. The empty class is vacuously a subclass of every possible class. The second is the universal class, denoted by 1, or U, representing the absolute totality of all objects under present discourse. Every conceivable class within the domain is, by definition, a subclass of the universal class. Therefore, the relation 0 is a subclass of 1 is an inherent truth. 1.4. The class complement. The operation of complementation defines a unary operation upon a class. The complement of a class A, denoted as A', constitutes the set of all elements within the universal class, 1, that are strictly not members of A. This operation establishes a dichotomy. Every object in the universe belongs exclusively to either A or A'. From this definition, it trivially follows that the complement of the empty class is the universal class, 0' equals 1, and conversely, the complement of the universal class is the empty class, 1' equals 0. Furthermore, complementation is an involutory operation. Applying it twice yields the original class, A'' equals A. 1.5. The operations of union and intersection. The algebra introduces two fundamental binary operations. Union. The union of classes A and B, A union B, yields a new class comprising all elements that are members of A, or members of B, or both, the logical inclusive OR. The operation is inherently commutative. A union B equals B union A. Key identity properties include A union 0 equals A union 1 equals 1, and idempotency, A union A equals A. Furthermore, the union of a class and its complement exhausts the universe. A union A prime equals 1. Intersection. The intersection of classes A and B, A intersection B, yields a new class containing strictly those elements that are members of both A and B simultaneously, the logical AND. This operation is also commutative. A intersection B equals B intersection. 1.6. De Morgan's laws. De Morgan's laws represent a pivotal theorem demonstrating the duality between union and intersection when mediated by the operation of complementation. They formally state that the complement of a union is equivalent to the intersection of the individual complements, and conversely, the complement of an intersection is equivalent to the union of the individual complements. A union B prime equals A prime intersection B prime. A intersection B prime equals A prime union B prime. These laws are foundational for simplifying complex logical expressions and designing digital logic circuits, as they establish how logical operators transform under negation.